Hi all, I thought I'd do a follow-up kind of example of this question here, which in the practical session we noted was not overly friendly. It does have a simplification, which escaped me at the time, but it's a good example of in this unit there's going to be lots of situations where we're looking for simplifications like this. So pretty much the most important thing that you need to be able to do, and it comes up all of the time because remember a lot of our concepts are associated with this magnitude of the different components that we have. So we're always going to have things like this. So what we're often doing and often need to do is take out some common factor of all of these terms, and it itself will be a perfect square, so it'll then be able to kind of escape the square root. And inside, that'll allow us to factorize these as a perfect square as well. So this is how we get simplifications. Now, all simplifications mean is that our numbers end up being nice and our equations end up being nice. In the real world, often whenever you actually have to solve these, as long as you know how to set up the equation, the computer does all of the solving and everything for us, so you just have to make sure you're setting it up properly, and whether the numbers are horrible decimals or irrational numbers or beautiful whole numbers, it doesn't actually make any difference to the difficulty in a computer being able to solve it. So let's have a look at this one though, because practice is good for being able to identify where we can make these changes. So firstly, in order to find the unit tangent vector, so we do have r of t, where r is a vector, and this solving, we get root 2, and e to the t, nothing happens, and negative, so e to the negative t becomes negative e to the negative t, like this. Okay. And then so we have to work out the magnitude, so working out the magnitude of this for our unit tangent vector, we get inside the square root, we get root 2 squared plus e. E squared is e to the 2t, so e to the t times e to the t equals e to the 2t, and here we get negative e to the negative 2t. Sorry, it'll become plus because we're squaring it. Okay, now we had originally assumed that there's not any great common factors here. There actually are. Though probably the easier way to see the common factors is in here. So we get 2 plus e to the 2t. And remember, this one over here is 1 over e to the 2t. So whenever we have a negative index, so we can think about it like that. So we can actually factorize out this guy here. So if we, and essentially we think of it the same as kind of giving all of these fractions a common denominator. So what I'll do, I'll get rid of this. And so what we will have, if we take, so let's do this all inside a big square root. So if we take e to the negative 2t out of all this, so this term here, outside of this, if we want to be able to know what we multiply this by in order to get it, it would actually be 2e to the 2t. Because remember, if we multiply this by this, we get e to the 2t minus 2t e to the 0, and we just get our 2 back again. So this one's 2 up here. So that'll be the term that we take out of there. For this term, it's actually going to be e to the 4t. Now remember, if we multiply this by this, we'll get e to the 4t minus 2t, we'll get our e to the 2t back. And then this term is our original term, so we get a plus 1 here. Okay. So, let me do the whole thing. This is quite useful. So now, this actually is a square. This is a perfect square. So this is e to the negative t squared. So it's going to be able to simplify inside that square root. On this one, this is actually a perfect square as well. So we've got a 1, we've got a 2. If we remember our basic polynomial of a plus b squared, we get a squared plus 2ab plus b squared. And so this one, sorry, I was writing it in the wrong spot. So this one actually factorizes out. This e to the 4t is the same as our a squared. This 1 is our b squared. And then this is our e to the 2t times 1. So we get e to the 2t plus 1 all squared. And so you can double check, if you expand this out, we should get e to the 4t plus 2 times e to the 2t plus 1. And so now these roots will have a nice simplification. And so we can get, here this will just be e to the negative t. This will just be e to the 2t plus 1. And that will be our magnitude. Okay, so it's good, it's handy. Now having said that, the numbers they still end up not being great when we put all of this in, but so we get here our t of t is 1 over, actually we can write it, let's write it this way. So we're dividing by our magnitude here, so that means actually everything goes the other way around, so we get e to the t outside of e to the 2t plus 1, and this is going to be outside, or like as a multiplier of our vector here, so just of our root 2 e to the t, move that over, root 2 e to the t, negative e to the negative t. And we can even see that some of these terms will have simplification. So this will just be a root 2 up here. This one will make it e to the 2t here, and then this one up here will be negative e to the negative t, so multiplying through, so it'll just become a negative 1. Now in the work solutions that I've got there, I have the rest of the steps, which ends up using the chain rule. So remember, chain rule is if we have u on v, then we do u derivative of u on v minus the derivative of v times u over v squared. And so it uses all this, and there's some other similar simplifications. I won't go through it here because I think you're probably just as well placed to go through that through the notes yourself, but of course ask any questions as well. I mainly just wanted to draw attention to this idea that of things that we can simplify, and this is usually in a lot of the questions that we have, this is what we're looking for. We're looking for an expansion that enables us to bring a square out of those brackets and get a perfect square inside the square root. Life doesn't always work like that, of course, and sometimes we end up with horrible square roots. And this question, if you look at the workings, still lots and lots of working, and because now we have to, so once we use this rule to find the derivative of the tangent vector, and then we're dividing through by this again. So, but it has a nice simplification at the end, so that's always satisfying when you get something like that. I hope you're all having a good week, and good luck for your assignment. Please let me know if you have any troubles. Bye.